I would like to add a few comments about when to use robust regression. Sometimes it's necessary. That's often because of the presence of outliers, which are sometimes just plain mistakes. And you might think that the best course of action would be simply to eliminate the erroneous data points. And in the case we just looked at, that's actually correct. But not all outliers are simple mistakes. Sometimes they represent genuine and important behavior of the system, but the distribution of the noise simply isn't normal. Also, it's not always clear whether a data value is an outlier or not. There's not universal agreement on what constitutes an outlier. Even if a data value is simply a mistake, and it's so extreme as to be visually obvious, we might be processing a very large quantity of data, including vast numbers of data sets. So many that visual inspection of all of them might not be practical. It is possible to define an automated routine to detect and remove outliers, but that runs the risk of missing some and misidentifying some others. Robust regression provides an excellent solution to that problem. Whether or not to use it may depend on inspection of part of the data. If outliers are found and seem to be affecting results, then robust regression may be called for. One can also analyze some of the data by both least squares and robust regression in order to find out how often and by how much the difference is palpable. When least squares and robust regression disagree too often, the reason should be investigated and robust regression might be called for. Finally, we're going to touch on a topic that is called nonlinear regression. The regression models we've studied so far are linear because they are linear combinations of test functions, which we can call trial functions. So they're linear in their parameters. But there are very useful cases for which the function which we intend to use to model our data is not linear in its parameters. This is the subject of nonlinear regression. As a simple example, suppose we believe the signal underlying our data is of this form. It's essentially exponential decay. It has two parameters, beta 1 and beta 2, but is definitely not linear in them. We can still fit the model by least squares by minimizing the sum of the squares of the residuals. But the solution is no longer so straightforward because of this nonlinearity of the parameters. In this particular case, we could log transform the target variable and get this. This signal function is linear in its parameters if we regard the logarithm of beta 1 as the first parameter instead of beta 1. So we could apply linear least squares to estimate them, but there's a catch. When we log transform the data values, we not only log transform the signal, but also the noise which is mixed with it. Hence, the noise will no longer follow the same probability distribution. In some cases, this makes the transformation impossible. If, for instance, the signal obeys that equation we just looked at of exponential decay, then all the signal values are necessarily positive. But if the data are signal plus Gaussian noise, some of the data values might become negative because of the noise, and if we try to log transform them, the result is nonsense. Furthermore, there are situations in which there is no convenient transformation which will make our model linear in its parameters. If, for instance, our model were some constant plus an exponential decay, then we cannot transform it to remove nonlinearity in the parameters. The usual approach is to solve for the parameters numerically. We could use a brute force approach, try a very large number of possibilities and select the one which minimizes the sum of squared residuals. But it's far more efficient to use some optimization search method, like the Newton-Raphson algorithm. Most statistical software includes functions which perform such optimization. Another approach is to abandon the least squares idea, instead adopt the maximum likelihood approach. As a very useful example, consider the case of logistic regression for binary data. In binary data, all the x values are either 0 or 1. which might represent two possible outcomes like failure and success. Suppose that the probability of success is some parameter p, and that it might depend on time, so p is a function of time. Then the probability that x equals 1, a success, is p, while the probability that x equals 0, failure, is q equals 1 minus p. The joint probability of all the observed values is the product of their individual probabilities. A very common model for the probability as a function of time is the logistic function. This can be viewed as a linear model of the log odds ratio. Here's a graph of the logistic function. As you can see, it looks kind of like a typical S curve. We have that Q, being 1 minus P, is given by this expression. And we can note that because e to the 0 is 1, the probability of a single observed value, which is either 0 or 1, can be expressed in this way. In this case, when x is 0, the top becomes 1, and the probability becomes the probability of failure. When x is 1, the numerator becomes this exponent, which is just p, the probability of success. The likelihood function is the product over all of the values of the probability functions for the individual results. And the solution for the parameters is obtained by numerical optimization in order to maximize the likelihood function. For logistic regression, the probability function is a complicated expression involving exponentiation of beta naught plus beta 1t. That's the kind of linear expression we used for linear least squares. We might also have used exponent of some different linear expression in parameters, like a quadratic function of time or higher powers. This is the logistic function of a more elaborate expression, but one which is still linear in the parameters. In such cases, there is a transformation called the link function, which relates the model we're fitting to an expression linear in the parameters. Such models can be called generalized linear models, not to be confused with general least squares. Good software like R can fit generalized linear models. In addition to specifying the expression which is linear in the parameters, you also need to specify the link function to use. It will perform the optimization needed to find the best parameters for you.